On. All right, there we go. All right, sorry about that. All right, course recap. So we learned a lot this last, 4 months, 3 months? So we get to recap our journey and begin our review process. So here is one of the slides at the very beginning of the class saying what an operating system does. So it manages resources. You have applications that you knew from your intro course. I guess this one's ECE specific, not EngSci specific course numbers. And I have to go complain at the EngSci people because you didn't have anything really in second year. So that is one of the things I will do in the summer. So I will try and remedy that or see if anything can be done about that. But this is how it looks like. You start off writing C, their application, they're using the operating system even though you might not quite know it yet. Then you would maybe had a hardware course that teaches you a bit about hardware. And then we have the operating system, which sits in between. And we know the two major parts of our operating system are kernel and library. And we all like kernel stuff because that's what we spent most of our time discussing. So there's three main concepts in this course. Virtualization, so we just share one resource by mimicking it, thinking it has multiple independent copies. We did this for literally everything. So we had like virtual registers to mimic having multiple CPUs. We had virtual memory that mimicked every process having access to all of the memory. And then we wrapped it up with a virtual machine. We just virtualized the whole machine, and then we can have multiple operating systems running. The next topic, which was, I'm sure, everyone's favorite, was concurrency. So that's handled multiple things happening at the same time. Main concern there is data races. So data races, two concurrent accesses to the same location with at least one being a write. If I know that off the top of my head, so should you. And to go ahead and fix that, we had to have some type of synchronization. Main one was mutexes to make sure that only one thread is running that code at any given time, so we don't have any concurrency problems. And then we also saw like ordering with semaphores, condition variables, that fun stuff. And then we also noticed that if we had multiple mutexes, we can potentially deadlock our code, and that means it can't make progress anymore. So concurrency, lots of fun. Then we ended up at persistence, so talking about file systems, disks, RAID, all of that fun stuff. Hopefully you're mostly done with Lab 6. So that's a file system. That's just how you organize files on disk or organize the data. So going all the way back, so now this was like one of the first slides in the course. Now we can actually kind of understand all of the CPU modes because we visited them all in the course except for machine mode. So machine mode's like the most privileged instruction mode. It doesn't have virtual memory or anything, but it's more set up like when you're booting your computer. And then there is a more privileged mode called hypervisor mode, and that would manage virtual machines. And then what is less privileged than that, but can still interact with hardware, is kernel mode, might be called supervisor mode, that can access hardware directly. It is the thing that is managing virtual memory and deciding which process to run when. And then user mode, that's where all your application and libraries use. It can't interact directly to the hardware. It has to ask the kernel to do things for it through system calls. So there's different ways to figure out, or different ways to architect your kernel, because we said that, hey, what's part of the kernel? It's whatever code is running in kernel mode. So there are different things you can put in kernel mode, and that depends on your kernel architecture. So if you have a monolithic kernel, you're pretty much putting most of the operating services directly into kernel mode. So that would include things like virtual memory management, process scheduling, inter-process communication, file systems, device drivers, they would all be done in kernel mode. So they're all running in that privileged mode. You have to do system calls to go ahead and interact with any of these. And this is what the Linux kernel is, and hand-wavy other ones. So the other extreme from this is called a microkernel, and that is trying to run the minimum amount of services in kernel mode. So the minimum the kernel has to do is deal with virtual memory, deal with process scheduling, and some basic form of IPC, and then you could actually implement your file systems and device drivers and other things in user space, but it would all have to go through the kernel through like the basic IPC mechanism. So it's a bit slower because, well, everything would have to go through that system call interface, which is a bit slower than just actually using functions. And this architecture, not really used that much. So like Mac OS will put things like device drivers in user space because, you know, the Mac OS kernel is sacred, so you can't touch it or modify it or do anything. So you can have architectures that are in between monolithic and microkernel. They're just pretty much the two extremes. And then we talked about libraries briefly. So the kernel is definitely part of the operating system, but what else you consider part of the operating system kind of depends on what applications you want to run and what libraries you might need, like depends on the application. So like things like Network Manager that manages like your Wi-Fi and everything, like what network you want to connect to, might use different libraries than, say, Firefox, which probably draws a user interface for you and uses the network, blah, 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 and all that stuff. So all those libraries may be considered part of the operating system depending on what you want your application to do. Because like, I don't know, your Android phone, that runs a Linux kernel, but you'd probably say it's a different operating system than your Debian virtual machine because, well, you run Android applications. Debian doesn't really run Android applications, so you might consider them a different operating system for that. But if you just ran Hello World, they could both just run Hello World, and they would behave exactly the same. So maybe you don't consider they're different operating systems if you just care about like command line things, although kind of a pain to use on your phone. So then we talked about processes. So the operating system, more specifically the kernel, has to maintain processes, which all the information stored in a process control block. That would include all of its state, so like all of its like current registers, all the virtual memory we now know, like the open file table, everything like that would be stored in that process control block. And we have to create new processes. And anyone remember the system called to create a new process off the top of your head? Fork, yeah. Only way to create a new process creates a new process that is an exact copy or clone of whoever called it, and they are independent throughout that point. And that's just with Linux and Unixy systems, that's the only way to actually create a new process. If we want to run a different program, well, the kernel is going to have to like reinitialize that block and load into memory all the details about that program and everything, and that's done with the exec.ve system call, so that's how you can run a different program. So then we had the cool terminology where you could have a parent with an orphan and zombies, and you can kill your children and all of that fun stuff. So we realized we're responsible for managing processes in Unix. We have strict parent-child relationship. So the newly created process is the child, and the parent has to manage it. So you should be able to identify and prevent zombie processes. So zombie processes is when the child has died and you have not acknowledged it yet. So it's still consuming some types of resources, at least its process ID and like exit status. And then we had orphan processes, so that's where the parent terminates before the child. So the child has to get reparented, likely it'll get reparented to a NIT, or a sub-reaper if there is one in the case of what you did in lab 2. And then question, we know that the user and supervisor communicate via system calls. How do the other modes communicate, aka super to hypervisor and hyper to machine? So they communicate exactly the same way as you communicate from user mode to kernel mode, but instead of a system call, there's just another special instruction, so it'd be called like a hypervisor call or a machine mode call. And it's pretty much exactly the same way, and there's different interfaces defined for that, which we didn't go into because we didn't go into how they're actually implemented, but the idea will be the same. All right, then next we did IPC. IPC was lots of fun, so read and write through file descriptors. File descriptors could represent anything, including a regular file, which we kind of now know how it's represented now through an inode. And then we could redirect file descriptors for communication. So like just making one process's standard out go to another standard in through a pipe. So that was one way we could communicate between processes. We saw signals, so you could send a signal to a process, tell them they should stop. They're technically IPC because you can send signals between any processes you would like. And there was a special signal to make sure we terminate a process, the sig kill, or kill -9. So that was a fun one. And signals are basically like interrupts. Then we transitioned to, well, we did a bunch of examples using pipes. We even did a brief detour on sockets and all that fun stuff, but we kind of took a detour before we started threads to talk about scheduling. Fairly boring, fairly straightforward. Had the first algorithms we looked at were like first come, first serve, which is just FIFO, AKA, I don't know, going to McDonald's or something like that. You're just in a line. Then we did shortest job first. That tries to reduce the average waiting time. Then we added preemptions and did shortest remaining time first. So if a new job came in that was shorter than all the other ones, we'd immediately switch to that. And that would optimize the lowest waiting time. Then we did round robin to try and optimize fairness and response time. So with all the scheduling algorithms, we tried to balance the average waiting time, the response time, so how long it took from when a process started to when it first ran, and then the fairness, aka how often you actually run it. And one thing we wanted to prevent was starvation, aka a process does not get to run at all. So we added more complexity to our scheduling, so we introduced priorities that also introduced priority inversion, which was another issue. So if a high priority process depended on a low priority process, well then you should probably treat, at least temporarily, that low priority process as a high priority process. So you can go ahead and clear that dependency, and then you can revert it back. So that was solved that problem by just doing priority inheritance. And then we discussed some processes need good interactivity, some others not so much, like maybe you only care about response time for programs you are interacting with, and then you have background processes you don't really care about, you just want them to finish quickly. Then from that point, we were only talking about single CPUs. We started introducing multiprocessors and said, okay, well, the dumb thing could do is just schedule them to CPUs as we have CPUs available, but now, especially after dealing with concurrency, you can imagine how that would be actually hard to implement and have locks around the whole thing, so it would be slow. So one thing they did was they just have a scheduling algorithm that only runs on a specific CPU core, and then we just switched around what processes are on what CPU. Briefly talked about real time, time for class. So briefly talked about real time. So that required some predictability. Linux, too complicated to actually do real time, so it does soft real time. But if you do embedded systems, you might have to start counting core times because you need a reaction within a certain time period. And then we briefly looked at Linux's current scheduler called the completely fair scheduler that tries to model the idea of ideal fairness, where every process gets approximately an equal share of the CPU time. All right, then we switched to virtual memory, everyone's favorite topic, or one of the top two at least. So how we did virtual memory was we used pages for memory translation, aka just big blocks of memory. So we divided memory into blocks called pages, and then we did our translation on a page level. And to do that, we used page tables. So our first idea was just to have one big table of all the mappings. So it was just an array of page table entries, and the page table entries, what they tell you is the physical page number that virtual page number is associated with, and all the flags, so whether or not it's valid to actually access, read, write, execute, and then some other ones we kind of experimented with. So like just custom bits you can use whatever you want for. So you use that for lab 3 to do copy on write. We saw the reference bit when we talked about the clock algorithm. So that's also one of the bits that would be in the page table entries that are populated by the MMU. And then, yeah, we discussed at this point, if we have one single large page table, then they're always huge. So we discussed multi-level page tables. And this is where the fun really started, right? So how we did that is we took our virtual address and we split it off into different indexes, and the number of bits we used for the index was determined essentially by how many entries we could fit on a smaller page table, and our idea was that each page table fits exactly on a page. So this was a lot of power of 2 math, but hopefully it wasn't too bad. So here, our page size was 4 kilobytes, pretty much is always 4 kilobytes for most systems. So that means that's 2 to the 12 bytes. So we need 12 bits to reference, an individual byte on our page. So that's why our offset was 12 bits. And then our page table entry in this case was 8 bytes, aka 2 to the power of 3. So we could fit 2 to the 9 of them on a single page. So that's why we had 9 bits for each level of page table. And the reason why we have 3 levels of page tables is, well, we wanted to support, in this case, a, 39-bit virtual address, right? 39, yeah. So this is a 39-bit virtual address. Why is it 39-bit virtual address? Well, that's half a terabyte or 512 gigabytes, and that's good enough for most current processes. If we determine that that is woefully inadequate, we would just add another level. So we just add another level, and then we can support a 49-bit virtual address, and that will probably keep us good for a while. But the reason we don't automatically just go to having 4 levels of page table is because this is really slow when you have to translate an address, right? To translate a single address in this case, I have to access the entry in the L2 page table, then look up what entry I need to access in the L1, then access what entry I need to access in the L0, and then I finally get the address I was looking for. So I turn like 1 memory access into 4 using this, which is really, really slow. If I added another level, that's just another memory access, and I turn it into 5 now. All right, any quick questions about this, our favorite thing? So then after we did this, we realized it was slow. We briefly talked about we don't have to write the translation, we just have to manage the page tables if we're the kernel. The MMU, or memory management unit, is hardware on your CPU that will actually use the page tables, which will do the translation for you. And in order to speed it up, it uses something called a TLB, or translation look-aside buffer, that is basically just a cache, so saves any recent translations you've done. So we speed up our memory accesses. So remember, we had that little program that accessed like every page. It was really slow, and then when it accessed everything on the same page, it was really, really fast. That was mostly because of the TLB and not having to retranslate everything over and over again. And that is also why they told you to like make sure all your memory is contiguous so it's really, really fast. Okay, that was a lie. They told you make sure it's contiguous so it's really, really fast, so it's all on the same page, not it has to be contiguous, because if it goes across the page boundary, that's more we have to translate, and that's basically why it's always slow. Otherwise, if you just use physical RAM, accessing memory is fast. It's called random access memory for a reason. So then we had a brief detour because I thought you needed a break from that hardship. So then we explored some questions. Yeah?
Just for like related to the TLB.
Yep.
Does it store like the entire virtual address, or does it like not include the offset when it's like stored?
So the TLB would basically just store the like page table entry associated with it.
So like PPM translation basically?
Yeah.
And you can use like the entire offset with the pages?
Yeah, so it wouldn't store the offset because the offset, the offset, whenever we do the translation, we never have to touch it, right? So it would just store, yeah, the PPN, it would probably just store the whole page table entry, so it has all the permissions and everything, but it would definitely store at least the PPN. And yeah, then we had other stuff with the TLB where if we context switch between different processes, we'd have to flush the TLB because remember, your virtual addresses, well, they're only valid for your process, so you probably shouldn't use another process's old entries in your process. So we had to flush the TLB, aka another word for just clear everything so that you don't use values for another process and all that fun stuff. All right, anything else with virtual memory? All right, mostly okay. All right, then we had a brief detour. We had the question using priority scheduling. And then we did mmap. That's not going to be covered on the exam, but that's basically a way that we can manage our own virtual memory. So we can ask the kernel to, hey, just map this file to memory so I can just access the file through memory instead of doing a read and write system call all the time. Just do all the mappings and handle it for me. So that was fun. Then we went to threads, and then things went downhill again. So then we had concurrency. So we had threads. We related them to processes. They are lighter weight. They share memory by default. So the only thing that's independent in a thread are its registers and its stack. Otherwise, they live within a process, so they share all the same virtual memory. They share all the same open file table. So that's all shared within a process. And each process can have multiple threads. Originally, you just have one to start. And that's where we had some concurrency issues. But both processes and kernel threads at least enable parallelization. So there's different ways we could implement our threading library. Most implementations map one user thread, aka like one of your P threads or one of the P threads to a kernel thread. So the kernel actually manages all the scheduling and things like that. And if we have multiple CPUs on our system, it can run them all at the same time, aka in parallel. And then, we also had like some complications with what would happen when we fork, when we have multiple threads or signals. If we have multiple threads and we fork, the new process that gets created only has a single thread, and that single thread is a copy of whatever just called fork. And for signals, if you have multiple threads and you send a signal to it, a random thread gets to deal with the signal. So that was fun. And the P-thread implementation was one-to-one. You also in lab 4 did user threads. So you just had one kernel thread, and then you implemented all of your user threads 100% in user space. So you just manage them through uContext. You created their own stacks, and then you manage switching between them by yielding and all that fun stuff that you implemented. So after we have threads, then we have synchronization issues. Biggest one being, oh wait, then we took another detour because I thought you needed a break. So we had another detour on sockets, and I showed you how to use a uContext. So you don't need to know sockets for the exam, but they're just IPC. Aside from the setup, which you would probably just look up anyways whenever you have to use them, you just use read and write system calls. They don't act any different, they're just IPC, but it might be processes on different machines. uContext would be fair game for the exam. It's basically the state of the user registers. I probably wouldn't ask anything too complicated, but it's fair game because you used it on lab 4 to implement your threads. Again, uContext was basically just all of your user thread or your CPU user registers. So like your stack pointer, your program counter, any other values in the registers. All right, then we had data races. And yeah, things went off the rails again. So we definitely 100%, a million % need to know what data races are and how to prevent them. That's like probably most of your exam questions. So we had mutexes and broke. All right, there, boom. All right, I fixed it. All right, I should stay out of my pocket. There we go. Okay, so any questions about this stuff? So lots of fun stuff. Questions like, hey, is there a data race in this code? Which, I mean, if I ask you that on an exam, the answer is probably yes. And then you fix it. So then that was data races. We also talked about how to ensure order because we had mutual exclusion before. The main way to ensure order between threads, so making sure one thing happens before another thing, we used semaphores. They were, basically they worked as like a atomic integer. So they had some initial value you can set, and then they had two fundamental operations. You could post it, which basically incremented it by 1, and then it had a decrement called wait, and it would atomically decrement, but the special thing it did was if the current value is 0, it will block and wait for another thread to increment it. The rule is it will never decrement it below 0, so it can never go negative. So it will block. You can force a thread to wait, and you can force a thread to wait for another thread to do some operation. The other thread posts, and then the other one gets unblocked, and it continue. Still have data races, still need to prevent data races. We saw some more advanced locking, so we went over condition variables. Might be clearer for more complex condition signaling. We briefly talked about like locking granularity. You had some practice with that in lab 5. So I told you to use one lock. You discovered it was slow, hopefully. And then I told you you can do whatever you want. what you likely did is you probably made a lock for each entry in the hash table, and then boom, it was a lot faster. Did anyone try making a mutex for each individual node in the linked list?
Initially, but then I was like, this is not worth my time.
So,
Went back to the previous.
so you didn't get it running?
No.
Okay, so you could have tried, I guess it was also hard to implement, but having a mutex for each node, kind of a pain to implement, as someone found out for you. And if you actually implemented it, you would probably find that that is really slow too. So yeah, because you just have way too many locks at that point. So there's some trade-off there, how many locks we have, how big the region is, so on and so forth. And then, well, we use multiple locks to speed things up. And then we have the situation where you would have to prevent things like deadlocks. Likely you didn't really have to do that in your lab, but that's another concern you would have. So you want to make sure that you don't try and acquire a lock while another thread has that lock, and then it's also waiting for you. So we needed what? Circular wait. So you need to have a cycle of locks. And then another condition is you have to have hold and wait. So while you have a lock, you try to acquire another lock. If you have those conditions, you can deadlock, and then we prevented it through breaking one of those. So we broke hold and wait with try lock. Remember, we tried to acquire that lock. If we didn't get it, we unlocked the one we had and then went to sleep for a little bit, then tried again. And then the other strategy we had is we just always acquired locks in the same order. That way we did not have a circular, any circular dependencies, so we were good. All right, and then we were done with the hard part of the course, joy. So then we talked about disks and enabling persistence. We talked about SSDs and RAID. So SSDs kind of like rammed, except they're accessed in pages and then blocks. So there are a bunch of pages on a block, and it had like weird rules where you would have to, you can only erase blocks at a time, and then you can only write to a page if it was freshly erased. So some complications there. The hardware would have to work with the kernel to get the best performance, aka trim, so you just tell it that you're not using a block anymore, and you kind of have to know which pages are on which blocks, and some minor details like that. The major part was using RAID, aka multiple disks, to tolerate failures and improve performance. So we went over a bunch of different modes. The first ones being like RAID 0, which was striping, aka, I don't know, I'll call it sonic mode. That was the gotta go fast mode. So you just striped your data across all of the drives. You could use all your data, but if you lost a drive, you lost data. So not really good if you care about your data, but if you want things to go fast, well, it was n times faster, where n is the number of disks. Then the other extreme was RAID 1, aka mirroring, so all your disks are exact copies of each other. So as long as you have one left, you're good, you don't lose any data. Then we talked about RAID 4, which introduced the idea of parity and had a parity disk, and said RAID 4 was stupid because everything was concentrated on that parity disk. It always had to be updated, no matter what physical disk you actually had the information on. So then we had RAID 5, which was the same idea, but it just distributed the parity across all of the disks. And then we had RAID 6, and then RAID 6 was 2 disks of parity, so that, well, you can tolerate up to two disks dying without data loss. And then we briefly talked about RAID 10 or RAID 1+0 or whatever you want to call it. That creates 2 copies of striped data, and the number of disks you can tolerate is kind of up to luck. So might be 1, but as soon as you lose like 1 pair of disks, then you're screwed. Then we had file systems to describe how files are actually stored on disks. So API-wise that we had looked at before, you can open files, change the position to read and write at through that seek system call that you're using in Lab 6 because you're managing a big 1 megabyte file. And then each process has like its local open file table, and the file descriptor is basically an index into that table. And then there's a global open file table that the kernel is managing for you, and that contains a pointer to a vnode, which represents something you can read and write to. If it's a real file, that vnode is an inode that we kind of know a bit more about now. And then it also has like the position and the permissions, so where in the file we would read and write to if we did a system call. And in order to store a file on disk, we went over a few different allocation strategy. Contiguous, aka just like an array, so you just pick the block it starts at, how big it is. We said that was a bit silly to do. Then we went over linked allocation, which is basically a linked list of blocks. Said that would be kind of slow because the pointers are stored on the blocks themselves. Then we did FAT, or file allocation table, which was the same idea, but we just used like a big array of pointers instead of having them on the blocks. So they would be a bit faster. And then we did indexed allocation that's basically like a big array, and then said that, well, that doesn't really work that well because we can't support that big of a file. So then we talked about inodes that are more of a hybrid, so they're more or less use the index strategy, except they borrow the idea from page tables and have multiple levels. But unlike page tables that you just have always 3 levels, or always 4 levels, if you have a 48-bit virtual address, it has varying levels. So in an inode, like the first 12 blocks are direct blocks that are stored on the inode, and then there's one single indirect block, so that points to a block of pointers, and then those pointers point to actual blocks, and then there's double, so it points to a block of pointers, which points to a block of pointers, which points to a block, and then it got up to triple, and then we figured that was good enough. That is big enough to support all the files we currently need. And on Unix, everything's a file named in a directory, can either be hard links or soft links. Most things are, and a hard link is basically just a name to an inode. You can think of a soft link as just a name to a name, but technically it's like a name to an inode, and then that inode has a name on it. So as you might have discovered from Lab 6, soft links, yeah, technically they're stored the same way, but you can think of them as name to name, hard link as name to inode. Yeah, I think that was that. So any questions about any of this fun stuff, or I guess Lab 6 is valid too. All right, so then we talked about page replacement. It was fairly boring. It was fairly straightforward. We saw some algorithms, so there was optimal. That was the one that we used for comparison, where we looked into the future, figured out what page to replace by what's not going to be used in the longest time. Then we did random. Didn't have an example of that, but it actually works surprisingly well because it's better than FIFO. FIFO sucks. But it's easy to implement, but had that weird anomaly where we had less memory and we had less page faults. So that gave us the solution of if we want our computer to go faster, we just get less memory, which obviously doesn't make sense. So not actually used. We talked about least recently used, which looks forward in the past to try and approximate the optimal. So you replace a page that hasn't been used in the longest, but it's expensive to implement. What we can actually implement is an approximation of least recently used called the clock algorithm that we did not that long ago. What was that, Friday? I think that's Friday. Saturday, last Wednesday? Something like that. Wasn't that long ago. So I probably don't need to go over all the details. There will probably be a question on this because, sure, why not? Then we briefly, oh wait, no, that was longer ago. Then we briefly talked about memory allocations. So the kernel doesn't have malloc or anything like that, so it has to implement its own. If you wanted to implement your own memory allocations, so aka any dynamic memory allocations, you have to be concerned with fragmentation. So fragmentation between allocations or blocks is called external. Fragmentation within a block is called internal. And there were 3 general allocation strategies for just any sized allocation you want. They all used linked lists. There was best fit, worst fit, and first fit. Then we talked about other memory allocation strategies. We talked about the buddy allocator, which kept things in powers of 2. And that was a linked list for each power of 2. Then everything's the same size. And the main idea behind that was to make merging blocks back together to be really, really fast. So every block of memory has a buddy. You split it off into 2. So if you and your buddy are free, you know you can merge them back together. And since computers like powers of 2, you can actually implement that very efficiently. Then we talked about a slab allocator, which is basically just allocating as if there were an array. And then we can just figure out what is allocated by using like a bitmap that just keeps a track of whether or not that index is allocated or not. Then we wrapped up and virtualized a whole machine that allowed multiple operating systems to share the same hardware. Idea, like with processes, to provide isolation between different operating systems. The hypervisor is the thing that allocates resources and actually controls the hardware. Type 2 supervisors, they're implemented in user mode, they're slow. Type 1 hypervisors need that hypervisor mode hardware support. There's some complications if they overcommit on resources, but you can physically move virtual machines to different actual physical machines because that's it's basically like context switching. And then we briefly touch about containers to have all the benefits of virtual machines without the overhead. Woo, and that's the course. That was the pretty much entire course, so I'll leave the few extra minutes for other questions, or let me know on Discord what we want to do in the last lecture. I assume questions probably on like virtual memory and concurrency and stuff like that, but let me know. I can also try drawing, so here's me trying to draw to like try and summarize the whole course in one little picture. I don't know how well it works, but bear with me. So like we had our registers in stack, and those together made up a thread, right? And then, well, in a process, there would also be a heap. So your stack and your heap are all in virtual memory, and that's managed by the kernel. And then other things in your process is the open file table. And one of those things, it could reference an inode, which is how you access the hardware storage through the kernel. And all of those are all in a process. So this big thing is in our process. And then in order to figure out what process to run, that's what scheduling is. So that's this. So your kernel also has to deal with scheduling. So that's dealing with which process to run. And that's basically figuring out which process should be executing on the CPU. So everything in red there is like actual hardware. So your compute would likely just be your CPU. And then we manage physical, so this would be physical memory. So that's managed by the kernel because each process uses virtual memory. And then managing this is done through page tables. That's also done by the kernel. And then inodes, they're on storage through a file system. And then the other part that's missing is when we had like multiple threads. So when we had multiple threads, what color should I use? So when we had multiple threads, that's when we had concurrency. Whoops, no T, concurrency. So that's where we had concurrency issues when we had multiple threads because, well, they were all accessing the same memory, which would be the same physical memory. And that's why you didn't have concurrency issues before because you didn't know about threads and everything was independent. So data races did not exist before because you only had a single thread. Anything else that should be added to that or like where anything else fits? And then, I guess I could draw a box around the whole thing and be like virtual machines. But that drawing-ish kind of makes sense. That's like kind of the whole course, right? You can point at pretty much any topic in the course and it's somewhat there, I think, right? All right, any other questions in our last few minutes? I have not started writing the exam. Yeah.
Is the final exam going to have a heavier focus on the second part of the course, or everything is weighted like pretty much equal?
Yeah, so how I write the exams, so we'll have that review, well, we can do a review session on Friday, and I'll think about the exam more, but generally how I do the exams is the midterm was mostly the first half of the course. So the final exam is everything, but since I already tested you on stuff, it's going to be weighted less heavy towards the midterm stuff.
But it's still there.
It's still there, yeah. The final exam is the entire course. So everything will be there. Generally how I do it is if there were parts of the midterm I didn't like or like things you did bad on, then I would include them in the final. So probably expect a virtual memory question. Yeah.
Will we also get like a sheet with all the functions that like are included?
Yeah. So like the midterm, I'll give you all the functions and everything like that, so you have them. All right.
Is it a programming course, like a programming question, or do we have to like?
Like where you program stuff from scratch? Probably not. At most, I haven't really done one, but at most, if I did one, it would be like a design this program question. Like, how would you do this? I don't care about you writing C code on an exam. Unless you want me to. Yeah.
How many questions will there be, like in terms of like major big questions?
Yeah, probably, I think, I forget. Most of the time there's a question on processes, question on threads. If you look at the past exams, I put like topic headers on all of them. And then like I'll do something about ordering, something about locking, something about deadlocks, something about files, something about, and then short answer questions that fill in the rest. A clock question, yeah, clock page replacement. I very likely do not need to write a scheduling question. Yeah, I think that's pretty much it. Unless you want like write me a C program and I will type it out, and if you have a syntax error, it doesn't compile and you get 0. No. Yeah, they're kind of silly.
And it would be great if you can go over some of the major topics you have in your head on Friday.
Yeah, if you want, you can ask me, like, spoiler alert, if you have a good idea for exam questions, I'd probably steal it and put it on the exam. I mean, I've written down some already. I just have to sit down and make the exam.
Okay.
But some questions are based off literally what I get asked in class.
Oh.
If you didn't notice that in the midterm. So, yeah, I guess we're out of time, so I'll be around. Again, just let me know on Discord. Look at the past exams, so 344 and this course, those past final exams, look at them. Any questions you want me to definitely go over Friday, just let me know. But so just remember, pulling for you, we're all in this together.